Welcome to part two of this lecture on the standard normal distribution, or the Z distribution, or others will call it the Z distribution. My name is John Walamuma. I'm from the School of Veterinary Medicine at the University of Zambia. So in this particular part, we want to just focus on the use of the normal distribution for converting raw scores from a normal distribution to percentile ranks. And so we'll also look at how you can convert the raw scores from a normal distribution into percentile ranks, and also how you can convert percentile ranks back into the raw scores. So that will be the major focus of this particular lecture. To start with, I want us to look at the empirical rule. So by definition, when we say empirical, it means that it is based or concerned with or verifiable by observation or experience rather than theory or pure logic. So the empirical rule we are talking about is something that has been formulated as a result of the mathematic statisticians, making observation from experience and, verifiable data. They have seen certain patterns, and from these patterns, they have come up with the rules that, govern what we are going to look at. So this is applicable to distribution of measurements in a normal population. So the empirical rule is applicable to distributions of measurements in a normal distribution. And the estimate of the distributions, it should be of numerical data. Numerical data, that's what we're talking about. So this is the empirical rule, the measurements with a normal distribution. So it states that approximately 68% of the measurements will lie within one standard deviation below or above the mean. And 95% of the measurements in a normal distribution will lie 2 standard deviation below or above the mean. And likewise, 99.7% of the measurements will lie 3 below or above the mean. So graphically, this is how it will look like. So we are saying that we are saying that about 68% of the values in a normal distribution will lie 1 standard deviation below and above the mean. So now, if we have 68.1 observations lying below above the mean, it means that this 68 is separated into 2. Half is on the below the mean, and the other half is above the mean. So we have 34.1 below the mean and 34.1 above the mean. So together, this area is 68, approximately 68 will lie 1 standard deviation below and above the mean. Likewise, if we add 68.1, we add to this, this is 27, about 27.2. We add this to this, it should give us something like 95. So 95% of the observations will lie 2 standard deviation below and above the mean. So you can see 2 standard deviation below and also 2 standard deviation above the mean. So we have 95%. In other words, if we divided this 95%, we have about 47.5% on the left below the mean, and also 45 above the mean, and then altogether it becomes 95%. Likewise, we have got about 99.7, the 99.7% will lie 3 standard deviation below and above the mean. So if you like from here to there is 3 standard deviation below and above the mean. And as I say that once you have transformed the values, if you have a normal distribution, and then you use the formula for the z-score and you transform those values into a z-score, what you are going to get is a standard normal distribution. And the standard normal distribution, I mentioned to you that it ranges from about -3 standard deviation below the mean and also 3 standard deviation above the mean, regardless of the numbers that are there in the original distribution. It will always, once converted, it will come to this. And so then we say this is a standard. It has a mean of 0 and a standard deviation of 1. So, of course, when we say, from the examples that we're giving, if we say that 68% of the observation will lie 1 standard deviation above and below the mean. In other words, the range outside this, the area outside this is this. So if we say that we are interested in only the area 1 standard deviation below and above the mean, then the area outside is this. Similarly, if we are interested in the area under the curve, which is 2 standard deviation, if you look at this again, if we are interested in the area, just the area under the curve, which is 2 standard deviation above the mean, if that is our interest, then this area is about 0.954, and then this area will lie outside, our area or our zone of interest. So you see, this is where we normally get the confidence and the rejection zone. In biological sciences, we normally use 95% confidence level, and so this is where this concept comes from. In other words, we are interested in values, only those values which are 2 standard deviation below and above the mean. Anything else we reject is anything else outside the mean is this. So you see that this is our alpha value. So the probability that we are going to make an error is this. Is about 0.5% in this case, or is 5%. So this is 95% is our confidence level. Then it shows that we can actually make an error or reject the null hypothesis when it is true, and then that is the alpha value, which is about 0.5%. Similarly, if we put our confidence level at 99, if this is our confidence level, 99.7, in other words, we have the likelihood of making a mistake or the probability of rejecting the null hypothesis when it's actually correct, it could be is about 0.27%. So you see that when we increase our confidence level, then the likelihood that we are going to reject the null hypothesis when it is true, it reduces. And also when you reduce your confidence level, then the possibility that you are going to reject the null hypothesis when it is true actually increases. So if the response variable as a normal distribution, as I said, you can use the empirical rule to describe that particular distribution. So whatever values the normal distribution and the standard deviation have, the normal distribution is related to the mean and the standard deviation in the manner shown above. So that is the relationship. So we can then use this thinking or this understanding to estimate the percentile ranks. If the mean and the standard deviation of a normal distribution are known, it is relatively easy to figure out the percentage rank or the likelihood of an observation having a specific score. To be more specific, assume a goat weight is normally distributed. That goat weight is normally distributed with a mean of 80 and a standard deviation of 5. We have a population of goats, and these goats, the weight of these goats is normally distributed, and the mean is 80, and the standard deviation is 5. What is the percentile rank of a goat which weighs 70 kg? If we put on that normal distribution, we have the probability distribution function there, and if we put that, what we say, at what percentile rank does this particular goat fall? Taking into account that the 80 kg actually falls on what? On the 50th percentile. You know, the mean is the 50th percentile. So if the mean is the 50th percentile, what percentile rank is this goat which is falling at 70 kg? So this is a distribution, which the normal distribution, trying to show us the relationship between the z-score and the percentile rank. I told you, I mentioned earlier on that this is the mean, the central value, the peak here. So we have the 50 percentile rank. So the mean as the 50th percentile rank. And then if we say we have a goat and we want to know at what percentile rank it is, then we can use this thinking, this understanding, to estimate the percentile rank where that particular goat falls. Let me come back to the thought concerning the empirical rule. If you look at the empirical rule stated that 68% of the observations, they fall within one standard deviation. So if you carefully look at this, if you move from 0 towards the left, you are going to see -1. So this is -1. This is the one standard deviation below the mean. Again, you can go to the left, to the right, and see where 1 is, and this is the one standard deviation above the mean. So one standard deviation above the mean, and from one standard deviation above the mean, and also one standard deviation below the mean, the area here is 68 approximately. So if this is 68, which means on the left we have got 34, and on the right we have 34. So if this is 34, then if this is 34, from the right to the let me talk at the left, from the left of this mean to where -1 is, this area is about 0.34. This is 0.34. So in terms of probability, this area is about 0.34, or the area is 0.34. So if this is 0.34, what is the area which is further -1? So to get the area there, we have 0.34, we subtract from 0.5, which is the mean, or we can subtract 34 from 50, and we get, what we get is a percentile rank for the value that falls at one standard deviation. In this case, the percentile rank for the z-score -1 is 15.9, and we get this from that understanding of the empirical rule, that from here, from -1 to -1 is 64, and then we subtract what lies on the left side from 50, and then we get 15.9. Similarly, if an observation, for instance, falls on the one standard deviation above the mean. So if this particular observation falls one standard deviation above the mean, we understand that the area from the mean to one standard deviation is 34. So if this is 34, from one standard deviation to from 0 to 1 is 34, then we know that the percentile rank of this particular observation will be 50 plus 34, which is 84. So we say 34.1. So in this case, it will be 81.4. So this is a percentile rank on this particular observation or lie. So if we are to make calculation, for instance, if we're interested in making calculations, finding out the particular rank of an observation, and then we do calculations, then we find that this particular observation lies one standard deviation above the mean. Then you say what percentile rank that observation fall. So in this case, it falls on the 84.11 percentile rank. So that is how this is used. So in this case, for instance, we make calculations, and in our calculations, we find that this particular goat has a weight of 70, and the mean is 80, and then the standard deviation is 2, and then the standard deviation is 5. So we calculate and find that the z-score is -2. So the z-score is -2. So what is the percentile rank on which this particular observation falls? If I can go back to the slide, which I was just, okay, let me go back to the slide. Yeah, so what we are saying, we found that this particular goat lies 2 standard deviation below the mean. So you see, if you come to this table, the goat lies 2 standard deviation below the mean. So we said that the area 2 standard deviation below the mean and above the mean is 95. Is 95. So if this is 95, the area, if we divide this area into 2, then you find that the area from 0 to -2 below the mean is 47.5. Similarly, the area on the other side will be 47.5, so that when you add, it gives you 95. So if from 0 to -2, this total area is 0.45. So what rank is this at two standard deviation away from the mean? This is a z-score of 2. So for us to get this value, I imagine that we are starting from 0 here and going to yeah. So this particular value is we subtract 0.475 from the value 5 here, because from here to here is from the mean to up to the end of the left tail. This area is 0.5, and on the other side is 0.5. So what we do is we subtract 0.475 from 5, and what we get is about 2.5 or thereabout. Yeah. So this is then the percentile rank for this particular goat. So the goat which is 70 or is falls on the 0.5 percentile rank. Yeah, of course, that is an approximation. When you do the more precise calculate, you get about 0.35. So statisticians, as I say, they've made things easier for us. They have come up with these tables, which would help us, to estimate the percentile ranks of a given, z-score. So, for instance, in our case, we are talking about a z-score of 2. This what we have on the column, the extreme left column. These are z-scores, and what we have inside here, these are probabilities or percentages. Let me look at the one that is normally the conventionally used. Normally we use the 95% confidence level. I told you that when we use the 95% confidence level, we are saying that this at 95%, it means that two standard deviation of the observation lie below and above the mean, lie what? Within 95%. So 95% of the observations, according to the empirical rule, lie two standard deviation above the mean. So if that was the case, then if I go to two standard deviation at 2 z-score, this is a z-score, and what I get in terms of probability is this. Is 99.9772. So 0.9772. If you look at this this distribution here, it gives you an idea. What it is telling me that it is taking into account as the z-score on the in this case on the right side of the mean. So if I were to read the percentile rank of two standard deviation, the percentile rank for two standard deviation above the mean, it will be this value, 97.9775. This is the percentile rank for two standard deviation. Let me just go back to, I mean, it's okay to understand. Let me just give you the converse of this. If you look in the example that we just looked at, we looked at the value which was -2 standard deviation below the mean. So instead of a positive here, it was a negative. And we observed that it was the percentile rank for that particular observation was 2.3. So if you look at this value, because it's negative, all we do, we subtract 1.97 from 1, and then what we get is 0.23. So when you want to obtain the z-score for the negative, all you do is you subtract this from 1, and then it gives you the percentile rank for the values below the mean. So for -2, you see we got 0.23, which is this value. You subtract it from 1, and for the above the mean, we get it as it is, because this is the way this particular table has been designed. You will have to be careful when you are reading a table, because some of the tables you find that it is just shaded in the middle, and not the way through. So if it was just shaded in the middle, this value it was most likely to be about 95. If you have open space here and open space on the other side, then what will be in the middle will just be 95. But since it is all shaded up to here, then we take into account that this value is concerned. It includes not only half of the area, but it includes the entire value below this value. So you have to look at the particular table the way it's read. Some of them you find that it will give you half. It's only shaded half. They only deal with half of the table, and so you have to be very careful when you're looking at this table. So this is what we've been talking about. In the previous case, the goat was weighing 70 kg. We subtracted, and then we found that this particular goat actually falls on the uh, 1.3 percentile rank, and based on the understanding that I gave you, if you have been following. Okay, so if what about a goat scoring 75 kgs? What would be the proportion of area below 75 kg is the same as the proportion of area above 75. Oh, sorry, below 75. So the proportion of the area below 75 is the same as the proportion of scores below 75. So what we do in this case, we do the same thing. We calculate the Z-score. We have the mean 80. We subtract from 75, and then we get we divide by the standard deviation. So what we get is the Z-score, and this will give us 1. If you see that we get 80, we subtract from 75. What we get is actually is 5 here. 5 minus 5 divided by 5. This is minus 1. So when you divide minus 1 by 5, I mean, if you divide minus 5 by 5, what you get is minus 1. And then you go into the table and look at the Z-score, which falls on 1 standard deviation below the mean. So 1 standard deviation below the mean, if you remember well, so this is the calculation from here will give you one Z-score. So if you remember well, 1 standard deviation below the mean. Let me go back. 1 standard deviation below the mean. This is where we are now. This is I come back to this. You look at this. 1 standard deviation below the mean is actually 15.9 percentile. This is what we are being given here as 1 standard deviation below the mean. This is 2 standard deviation, then this is 1 standard deviation, which is 15.9 below the mean, and you can calculate this from the table so you can work it out this from the table. So the table, Z table, makes it easier for us to calculate this kind of thing. And it's the table that I was just showing you, and it can be used as long as the distribution is normally distributed. So you can see if you have the Z-score is 0, then the area to the right of the curve is 0.5, because the total area in the curve is 1. So if the Z-score is 0, then the area to the right is 5. If the Z-score is 1.65, then the area to the right is this. If the Z-score is 9.6, the area to the right of that is this. And of course, likewise, we are looking here at half of the curve. And then similarly, if the Z-score, now we are looking at the left of the curve, is 0, and then the area to the left is 5. If it's minus 1, the area to the left is like that, and you find this observation. So this particular Z-score is looking at half the area, not the entire, graph. So this, actually what we are saying is that this is, if you remember, we are saying that this is the 95% confidence interval that we normally use, the 1.6, yeah. So when when Z is negative, it means that that particular observation lies below the mean. Thus, a Z of 2, a negative 2, minus 2 means that the X lies 2 standard deviation below the mean. And the same, if the Z-score is plus 2, it means that it lies 2 standard deviation above the mean. Let's assume now that we have, uh, uh, we go back. Let's assume that we have another example where this particular goat is weighing 90 kg. We are looking at a goat that was weighing 70 kg. And you remember that the mean is 80. And we looked at a goat that was weighing 70 kg, and we looked at a goat that was weighing 75 kg. So the one that was weighing 70 kg was 2 standard deviation below the mean. The one which was weighing 75 kg was 1 standard deviation below the mean, given that the mean was 80. Now, how about a goat which is weighing 90 kg? So we do the same thing. We calculate the z-score, and this time is +2. So +2, then we have to go to the table and calculate the percentile rank. You remember what I said, the percentile rank is 0.997. This is the 0.997. And this is what you get, if you remember, 0.977. This is what you get from the table. If you go back to the table and you come to the extreme left of the table and look for 2. This is the z-score of 2. And then you look for, this is 2. So because it's 2, we just read in the first row. In the first row is 0.977. So this is the percentile rank for +2. If it was 2.201, I was going to come here. So these ones, the values on the top of the table are decimals of this, or they are decimals of what is on Z. So if you have, say, for instance, 2.9, then you have to come to, if it is 2.09, then you have to come to this last column. So these Z values, the values on top are supposed to be the other Z values. If you add, they are supposed to be added to this as decimal points. I hope that makes sense to you. Yeah. So because it's 2, which means it's 2 and 0, 0. There are no decimals there. So that's why I picked the first column. This 2 means 2.00. But this one, it will be, the next one will be 2.01. Like that. This next one is 0.202. The other one is 0.204. I'll read from this. So, but what I'm interested in here is that we obtained that the z-score for that particular goat, which was 90 kg, and thus it was 2 z-scores above the mean, so 2 standard deviation above the mean. The z-score is, the percentile rank for this is 0.977, and that's what is shown there. And if a goat is what goat, now let's look at converting from percentile ranks to scores. We are using scores to convert to percentile ranks. Now suppose you are given a scenario which talks about moving from percentile ranks to scores. Here the question is, what goat weight would include 70% of the goats in a flock? So what goat weight? Suppose we say we want to eliminate some goats and we want to only leave 75%. So we have a goat population and we want to remove some goats and we just want to leave 75%. And so this elimination will be based on goat weight. So now the question is, what goat weight would include 75% of goats in the flock? So we have to estimate or come up with the goat weight that includes 75% of all the goats in a population. So we have to estimate the 75 percentile rank and then see what observation carries that 75% percentile. So what we do in this case, we have the mean. Remember, we have the mean of 80 and we have the mean of of 5. So we compute this, using a reverse step. So what we do is we calculate we go back to the value. So from this, what we have the mean, and then we have the mean, which is 80, but we don't have the x. And then we have the standard deviation. But we have been given the percentile rank where this particular x falls. So using that percentile rank, it's easy for us to calculate x. So we'll calculate x, we'll identify where x is by using this. So we have, in other words, we have the z here, and we have so z will be derived from the table using the percentile rank, which is 0.75. And then we have the standard deviation of 5, the mean of 80. And so what is x? So you see, if we go to the table, we say that we find the z-score of this 75.75. And the value for 75, the z-score is what is 0.674. So this is the z-score for this particular percentile rank. I'll go to the table and show you how we get the 75% percentile rank, which we are saying is 0.674. Maybe let's just go to the table and look for the percentile rank for 75. 75, if I go to the table, 75. So we are looking for 75 percentile rank. So we go to the table. Our z-score is 6.74. 6.74. Okay. So I want to show you how we get this 6.74 from the table. So 75, we are talking about 6.74. So 6.74 is about here. Is about here. 6.74. If you follow where 6 is on the z score, you look at the z6. 0.6, you get where 0.6 is, and then follow that row, and then come where it meets 7, which is 0.67. Of course, this is not precise, the 4 is not there. So where it meets there, the percentile rank is this one, where it's written, where it is 0.7486, which is close to 75. So this is the closest number to 75. And so this is how we obtained 0.67. So we looked for 75, or the number closest to 75 in the table. And so this is the number. And then when we find this 75, or the number closest to 75, then we see where it lies. So it lies from only 0.67. So the row is 0.6. And the column is 0.07, and then we get that figure. That's how we estimate that. Okay? So we get the percentile rank for this, and then based on that, we get the z-score. Now we have the z-score. So we can put the z-score in this formula and estimate the row value. We have the z-score of 0.674, and then here we have got the x. This is what we are trying to derive. This is 8, this is 5. So when we calculate this, we find that the actual weight is 83.37. So this 83.7 if we use this as our cutoff point, then 75% of the goats will remain in the population, and the other 25 will be eliminated. So, this kind of thinking is used when you want, for instance, to get or to set up even the cutoff point. If you want to set up a cutoff point, and maybe you want a certain percentage of people to fail, a certain percentage of people to pass, because you have limited space, you use this kind of thinking, and then you use this as your cutoff point. If you use this, then you know that 75% will remain, and 25% will be, will fall off. So, of course, this is just the same thinking I have put here to illustrate what we've been talking about. I want to give you this exercise, and you work on it at your own time. Assume that for a population of Zambian adult pigs, the body weight is approximately normal. It's normally distributed, with a mean of 129 and with a standard deviation of 19.5. So this is the Zambian population. We are assuming that the mean is 127 and the standard deviation is 19.8. What proportion of pigs have the mean weight more than 167.8? So what proportion of pigs have more than a weight 167.8? So just to give you a hint, this is our mean, and then this is our x. So what you want to do is to find the percentile rank of this. So you have to estimate the percentile rank of this, and then once you find the percentile rank of this figure is, you can see that this is above the mean, and so then you are going to see what proportion of pigs have weight more than. So once you find the percentile rank of that, then you look for the area which is to the left or to the right of this percentile rank, and then you let's see what you find. So do this at your own time, and then submit to me through the Moodle platform. Okay. You can also work on this exercise in a population in which serum colostrum is normally distributed, with the mean this and the standard deviation stated. We might choose to find the probability that a randomly chosen individual has a colostrum more than 250 per 100 mils. So you have a normal distribution, and then we are saying that you want to see that a randomly chosen individual will have colostrum level above 25 milligrams per 100 mils. Okay, so you can work it out using the normal curve as well. Okay. The other thinking that can be used on this, of course, is the interval. We can use the z-score to estimate the area under the curve, and I've provided notes for this. You can go through the same. The thinking is the same. If you look at what we said, the area under the curve. If you talk about the area between one z-score below and one, the area between the one standard deviation and the other standard deviation, this area is 68%. So this area falls within 68%. So we can use this thinking, for instance, that if we want to set cutoff points, we don't want very fat. For instance, if you are dealing with chickens or pigs, you don't want very fat pigs. You also don't want very small pigs. So you want the area in the middle. And so you can use this kind of thinking to estimate the percentage. Say, for instance, we wanted the only pigs that are within 2 standard deviation, and then we can use this to estimate the weight, so that only pigs which fall within the 2 standard deviation weight, they are the ones that are included. Okay? So this is the thinking. So you go into the table. In this case, we're interested in the area under the curve within 1 standard deviation, and so you subtract the area on the left and the area on the right, and then you come up with the area in the middle. So the same can be done if it is 2 standard deviation. You can do the same. Okay? So I leave you with an exercise to calculate the area under the curve, normal curve, for 2 standard deviation. I have calculated for you for 1 standard deviation. How about the area under the curve for 2 standard deviation? Of course, there's an answer there for you to appreciate. So you can read these notes and you appreciate how the area under the curve can be used, to make decision. So this is just a graphical picture showing you area for area under the curve. Here is an example we can use to solve situations. We can use to solve, for instance, what proportion of goats weigh between 70 and 90 kgs. So if we're given a situation that can we find out the proportion of goats that weigh between 70 and 90 kgs. So we use the same thinking where we find the percentile rank for a goat at 70 and also the percentile rank for the goat at 90, and then we estimate the area between these 2 percentiles. So this one, of course, if it's in the other case, the other scenario, this one is 2 standard deviation away from the mean. This one is 2 standard deviation above the mean. And then so we are interested in the area between these. So if we say what proportion of goats would weigh between 70 kg and 90 kgs, what we do is that we find the percentile ranks for this and then find the area that is in between. So this is how we use to make use of the area under the curve. So what have we been talking about? We are talking about the standard normal curve, that the standard normal distribution, or the Z distribution, as a mean of 0 and the standard deviation of 1. And this distribution can be used to compare 2 or more distributions. And also the standard normal curve distribution can be used to estimate probabilities, like the way the examples have been given. So you can estimate or compute probabilities of the events involving normal distribution. Thank you for listening.